All right. So welcome to the recap lecture. Before we begin, are there any questions regarding the topics that we have covered? Probably any questions on the homework, problems, or anything? Okay. So actually, I want to just to make a recap for the entire for the entire course of lectures today. I think I will. So regarding the final exam, right? I guess that's something that is everyone is interested in. So there will be some topics that have been covered in the first quarter, and there will be topics but there will be more topics that have been covered in the second quarter. For sure, you would like to know how to solve all of the problems from the homework. That's something that is definitely going to be useful. And also take a look at the examples that have been covered on the lectures and the discussion sections from the discussion slides. I know that the discussions have not been posted, and so I was thinking about going over some of the discussion slides for you to repeat that. But I guess it will be better to start with repeating the material from the very beginning. So in the very beginning, we were discussing the problems, the formulations for the problem, right? I remember that on the midterm there were difficulties with the notion of a formulation. Just for you to remember, a formulation is essentially a polyhedron that like a formulation for a set X, which is a subset of a mixed, which is a mixed integer set. It's a subset of Zn times Rp. If only if the set X is an intersection of the polyhedron P with the set of. Let me actually try to highlight what I'm talking about. So I'm talking about this definition. There is formulation. Formulation is a polyhedron P, such that, and we said that the polyhedron P is a formulation for set X if only if X is representable as the polyhedron P intersected with the mixed integer like lattice. And we also have the notion of an extended formulation that is tightly related to the notion of projection. So we say that a polyhedron is an extended formulation, probably in a more like in a larger dimensional space or an elliptic space, if after a projection of this polyhedron onto a lower dimensional space, we get an actual formulation for the set X under consideration. And then we have introduced some notions about which formulations we consider to be good or bad, or which formulations we consider to be better than others. And we have figured out that the best formulation we can ever achieve is a formulation that exactly coincides with the convex convex whole of the set X, right? This is the best formulation, and therefore we call one formulation better than the other if they are nested into one another. And from like basically the later part of our discussion about COTS and balance inequalities is very much related to this notion of a better formulation, because basically introduction of COTS, introduction of balance inequalities brings you closer, brings your formulation closer to the ideal formulation for which the solution of the linear programming relaxation coincides with the solution of the original problem. Right. We had a couple of interesting examples, in particular the uncapacitated lot sizing problem, for which we have given explicit formulations, like a bad formulation, and then a better formulation, and a standard formulation as well. I would suggest you to recap quickly what exactly what were the other examples of the common problems that we had. For example, the traveling salesman problem. What was the problem itself? How we formulated it? What was the eventual formulation that we have come up with? We have had like a semi formulation, like an incomplete formulation that we completed the formulation with additional inequalities, and we have discussed later, first during discussion about the computational tools, and later when we were discussing algorithms for the difficult problems, we have discussed methods in which we can utilize this inequalities, even though there are a lot of them. If you remember, is anyone remember? Does anyone remember that the point when we discussed how exactly we can use these inequalities, even though there's an exponential number of them? Okay, you remember? Anyone else?
I remember the exponential, but I don't remember how.
Yeah. So basically, what we discussed was that this inequalities, each of them is prohibiting a single separation of the entire graph into subtours. So basically, the problem with the original, if you remember, the problem with the original incomplete formulation was that a solution like this is considered to be a feasible solution for the incomplete formulation. And then each of this inequalities for each s, but essentially there is a particular subtour that is being violated. There is a particular subtour that violates this particular constraint. For example, if we take let's draw the graph. I think that there was a graph like this. Had a subtour. Right, and we have for example, so the first cut set constraint tells us that a salesperson must leave at least once from each group of cities. Basically, S is the group of cities under consideration, and this inequality is telling us that the summation over all I, the summation over all J, the summation of all I's that are inside the set S, and the summation over all J's that are outside the set, Xij must be greater than or equal than 1, meaning that there must be at least one edge. For example, if we take this set of nodes as S, there must be at least one edge that is going outside, from the set S, right? And so in this particular case, this particular splitting of the entire graph into subtours is being violated, is violating that particular inequality. Therefore, this inequality, an inequality that is defined with this particular set F, is a cutting inequality, like a cutting plane for a solution that corresponds to this this collection of subtours. And we can make sure that this solution is infeasible by adding a particular inequality. So, for example, if we are solving a problem of this sort, and we have got a separation, like a solution like this, then we can take any subtor, make it yeah, make that regular, and then resolve, and we can keep adding we can keep adding the inequalities to the original problem, improving formulation with every iteration.
So we start with this one, solve it, and then check if there's subtours.
Yeah.
And then if there's a subtor, take the first subtor, and then add that the cut set inequality, which makes it so that for the specific subtor S, that subtor can exist. So you wouldn't add it for all the exponential combinations of that. So you'd only add it for the ones where you want that issue and then you want it again. So in that case, like a lot of cases, you'll get rid of this couple subtours and then we'll have the correct answer.
Right.
So we don't have to do exponential, but in the end, though, it's like there are cases where you'll run through every single process.
Yeah, it is possible. That's why, but it is kind of inevitable because it's an NP-hard problem.
That's where it's still NP-hard, but in practice we're able to get it.
Yeah, precisely. Yeah, and we have, so if you remember an example that we have shown, like a computational example. I was showing actually two examples on the during a lecture. In the first example, we branches. Okay. Yeah, so there is a notion of linear programming relaxation. There is also a notion of combinatorial relaxation. They're not like they are different in formulation, but both of them are kind of considered to be easy problems to solve. After that, we have discussed. So after we have completed the topic about the formulations and the relaxations was the first topic regarding the dual bounds, and then we actually and then we have switched to a different approach to constructing dual bounds, which is the Lagrangian relaxation and the Lagrangian dual. We have discussed like the general composition of a Lagrangian relaxation, and then we realized that there is an entire space of possible Lagrangian relaxations that you can consider, and in that space, some Lagrangian relaxations are better than others, and from that we recovered a notion of Lagrangian dual, which is a notion of which is an optimization problem in the space of Lagrangian relaxations, which aims to find the best Lagrangian relaxation. Is there anything that needs to be repeated here? What do you say? Okay. It is important to recall the notions of a dual problem, just for you to recall that. So we call that the two problems are called are forming weak dual pair if for all x, like if we have the two problems. One is the maximization problem of C of x over all x's, and the other is the minimization problem for omega of u over all u's. We say that they form a weak dual pair if C of x is less than or equal than omega of u for all x's and for all u's. And we say that they form a strong dual pair if the optimal solutions to these two problems actually coincide. Yeah. This is something that definitely needs to be remembered from the course. And then we have seen some other examples of duality, like Lagrangian duality is obviously an example of duality, but also there are other examples, including the maximum cardinality matching and minimum cardinality covering. Okay, so after that, we have completed the topic of dual bounds. We have switched to the topic of primal bounds, and the first thing that we have seen is that the topic of restrictions, which is basically the opposite of constructing a relaxation. Restriction is the opposite of a relaxation. And then we have switched to looking into at heuristics. We have realized that the only way to construct a primal bound is to actually find a feasible solution, and for that there could be some algorithms that are not guaranteed to find us an optimal solution, but at least finds a good feasible solution. And some of the heuristics were the rounding, also the greedy heuristic, which is the very interesting and important heuristic. We have seen an example of a greedy heuristic, specifically for constructed for binary knapsack, and I believe that during one of the discussion sections, we were able to see how for some problems, so basically greedy heuristic for knapsack is providing us essentially a very similar solution to a solution that is being provided to us by a linear programming relaxation. This is an non-trivial fact by itself. It needs to be proven. We have commented on it. I think I proved it during one of the discussion sections. But the only what can be there was a difference between the solution that you get from the binary knapsack problem and also the solution that you get from an LP relaxation. What was the difference? Do you remember? The difference was that, LP relaxation is a relaxation, therefore it doesn't have to be feasible. And so one of these numbers that are 0 in the greedy heuristic approach can be fractional, actually, which makes it an infeasible point. But the position of these ones is basically the same. Okay, so this is regarding the greedy heuristic, and also we have had other heuristics such as local search and the taboo search, which is the improvement over local search, simulated annealing, and the genetic algorithm. I don't think we will have particular problems for them in the final, but they are very important examples of global heuristics for global optimization in many aspects in different applications. Okay, so after we have considered the primal bounds, we have switched to looking at the examples of problems that are solvable via simple polynomial time algorithms. For example, those that are based on the algorithms used for bounding, for obtaining dual bounds and primal bounds, such as the LP relaxation and the greedy heuristic, and also some other types of algorithms that are not usable for obtaining bounds, but also very important in practice, such as the dynamic programming algorithm. We have seen the conditions for which an optimization problem needs to satisfy in order to be solvable via, for example, a linear programming relaxation. The main example, the main property that we have seen was the core metrics, the core value of the problem having a totally unimodular matrix, which has very simple sufficient conditions that are easily verifiable. We have seen the examples of totally unimodular matrices, for example, in the minimum cost network flow. And we have seen an example of a formulation of a minimum cost network flow, both during the lecture and also during the discussion section. I would like to stress here that it is an extremely important type of problems, because it's very common in logistics and in floor scheduling and in planning, and you do need to practice that, because we have spent a considerable amount of time, and that's not something that has been covered by the midterm. So I like definitely in some way there will be something that is related to this topic of problems being able to be problems that are solvable via linear programmable relaxations, such as minimum cost network flow. There were other examples, like, so here I can go through this example in particular once again if you don't remember anything about it. But there were also more specific examples discussed during the discussion section, so please make sure that you repeat that. Does anyone want me to go over this example once again? Cool. So we have seen the example of how to prove duality for max flow min cut using the notion of total unimodularity. So that was important theoretic application, and after that we have seen the problems that are based on the problems whose solution is based on the idea of dynamic programming. And for that, we have discussed several different examples of the problems, starting from the shortest path problem and going to uncapacitated lot sizing, and also optimal subtree problem. We have constructed this small little principles of optimality, which essentially the most important part in the solution of the problem using dynamic programming. It's basically the core of any algorithm that is being based on the idea of dynamic programming. And it's very important for you to remember and understand how exactly to construct these principles of optimality, what they are, in their core, and how to use them for dynamic programming examples. Does anyone want me to go over an example of a construction of principle of optimality? Does anyone remember anything about construction of the principles of optimality? You remember? So okay. Let me actually pick a topic and go over that.
I think the principle of
Yeah, it's definitely the case that not all of the integer programming problems are solvable with the dynamic programming approach. Although those that are, for them, the dynamic programming approach is definitely very much usable. That's basically why this topic, like the dynamic programming subtopic, is related to the easy problems part of our course. It's because it's only for those problems that are easy. But I would like to say that even for problems that do not have like an obvious structure of like an obvious graphical structure, such as the optimal subtree problem or the binary knapsack problem. Binary knapsack is definitely a very important example of it. You still are able to construct dynamic programming principle. If you would like me to, I can go over, for example, the construction for the binary knapsack or for the optimal subtree problem, because I think it's important to understand if you don't remember that. What about the binary knapsack then? Is that an obvious? Okay, so let's see what we have here. So basically, what we want to construct is a relationship between the solution to our problem for a larger size of the input through a solution to our problem for a smaller size of our input, right? That's the principle. That's what principle of optimality really is. So let's say that we have positive integers aj's and a number b. We have a binary knapsack problem that is asking us to find a binary vector of size n, a binary vector x of size n, such that a linear function of this is being maximized, subject to a single linear inequality, aj xj less than or equal than b. And one important part here is that our b here is not a very large number, and so we have an opportunity, like we have an option to actually consider all of the numbers between 0 and b. So let's say that our lambda is a number between 0 and b, and we have another let's take another variable r that is between 1 and n, and we define a problem PR of lambda, which is aiming at maximizing of a binary vector of size r now. So the size is being reduced of the very much the same of basically a truncated objective function, subject to an inequality, and linear inequality that has been truncated, and the right hand side has been reduced, so the capacity has been reduced. Basically, if your initial objective function was 1, C2, 2 plus and so on, C and xn, and then you had a1 x1 plus and so forth, and xn less than or equal than b, where b was like a larger number. Now it's like this part has been reduced to this one, so now it's only c1 x1 plus and so forth xr cr xr that is being maximized. And also you have a1 x1 plus and so forth a r xr that is being less than or equal than lambda that is smaller than this b. So for the inequality, we'll also have taken only part of the inequality instead of taking the entire inequality. So obviously this problem is of a smaller size than this one, but they are very much related. So basically, the first step in making up a principle of optimality is understanding what is the problem of smaller size that you will be able to leverage, solution for which you will be able to leverage. Are there any questions on this step? Then we consider a solution x star of this PR of lambda, of this like reduced or smaller problem, And we consider two cases. If xr, which is the last component of the vector x star, so xr star is equal to 0 or xr star is equal to 1. There are only two cases to consider actually. And if xr is equal to 0, then xr of lambda. So let's see. Let's say that we have this is our vector 0, 1, and so forth, and then there's the component r, and it can be either 0 or 1. This is our x star. So if xr is equal to 0, that basically means that in like out of r different objects, we have decided not to pick it anyway. We really don't care if we do have that object or not. And therefore, if we just didn't consider picking up that object, it wouldn't change our solution. And therefore, fr of lambda must be equal to r minus 1 of lambda, right? If we did pick that that last item, then fr of lambda, then like if we decided to just not consider that last item, we would have to we would need to basically reduce the size of our backpack in accordance to have shrink the amount of possibilities for us to consider. Then fr of lambda must be equal to cr, because we got rid of the last item, plus fr minus 1 of lambda minus ar. Right, and now we are ready to formulate the principle of optimality that is telling us that fr of lambda is equal to either this guy or this guy, depending on which one is larger, which is basically what's written here. And this essentially defines to us the solution to a problem of a bigger size through a solution to a problem of a smaller size, which is the f of r minus 1 of lambda and f of r minus 1 of lambda minus ar. Are there any questions? I don't think. Okay, so basically this is the general rule of how you construct. This is the way it's done for the cases when you don't really have like a graphical representation. It is important to understand that it's actually possible. Like once you have done this entire line of thinking, now you can actually construct a graph. You can actually construct a graphical representation like this one that corresponds to that principle of optimality. But it's not necessary that you first construct a graph and then you have to construct the principle of optimality. It can go the other way around, and most commonly it goes the other way around. Okay, any questions regarding dynamic programming? Yeah, and then we have considered another class. So up to this point, we have considered easy problems that are solvable with linear relaxations or just relaxations, like any kind of relaxation. So basically, you're taking relaxation of a problem, which is an easy problem, a polynomial time solvable problem. You solve that, and you accidentally end up with a point that is feasible for the original problem. That means that you have solved the original problem. Then we have considered the problems that are solvable with dynamic programming, which is a separate kind of class of algorithms that you don't normally use for bounding, only for the exact solution. And then there is a class of problem that is solvable with algorithms for that are normally used for primal bounds, which are basically the heuristics that we are using. And this class is being constructed out of problems that have some properties, which is, for example, the submodularity property. We did not speak too much about it, but it's important to know that such problems exist, and they are forming a very important like class of mathematical objects actually. There is a very deep theory about the geometry of this problems. Yeah, so as an example, we have seen the maximum spanning tree, and we have seen the example of its solution with a greedy algorithm, which gives us the exact solution to the original problem. Okay. Are there any questions regarding? So this, like at this point, we have finished the first quarter, and there will be some problems from the first quarter that will be included into final as well. Just wanted you to recall what exactly you probably still want to repeat. Then let's switch to the second quarter. In second quarter, we were focusing at problems that are not generally easy to solve, but still solvable with like we still need to solve it, right? We really don't know what is the correct what is the correct algorithm, what is the correct polynomial time algorithm, but we just want to know any algorithm. And the first idea that we have discovered for ourselves is the idea of branching, or the divide and conquer principle. We have learned that just branching is not like even though it is solving the problem, it is normally extremely difficult and extremely long. Like it takes an extremely long time, and therefore we have added to the idea of branching, we have added the idea of bounding. Like we also call that the implicit enumeration. It's based on the idea of pruning by three different kind of principles. First is the principle like pruning by optimality, pruning by bound, and pruning by infeasibility. Essentially, these are the three main like ways of pruning that you need to know, and there's not much that can be done in order to like add more of these principles. However, there's actually much more that can be done to the ways we are branching. So the question of bounding is not really like doesn't have too many options for us to choose from, but the questions of branching is something that we definitely can explore. And also the questions of how exactly we solve for dual and for primal and dual bounds is extremely important. Let me actually come back here and comment on this a little bit. So on pruning, basically for pruning, you can see that we are normally using the upper and lower bounds for the solutions of different problems and subtasks of the integer programming problems. Therefore, we are always interested in coming up with as good bounds as possible. At the same time, we don't want to spend too much time on the same bounds, right? And for that reason, we have had different there is a space for maneuvering, for designing more more adapted algorithms, depending on how exactly you choose ways to enumerate, ways to branch a problem into subproblems, and how in which order you examine these branches, and which how do you distribute computational time between computing bounds as tight as possible, or as much as possible, like as many bounds as possible. Okay, and then we have had an example. So I think it's it's probably more interesting. I don't think there will be too many questions on how like on the different types of branching, like the special order set. Although it is definitely an interesting topic, and orbital branching as well. But I think that it's much more important for the purpose of the exam, at least, to understand how exactly the normal the very basic algorithm works, how exactly the normal algorithm that is based on LP relaxation works. So I was thinking about actually showing you either an example that we have had on like during the lecture, or switching and showing you a different example that I have had during the discussion section. Should I do that just to remind you? Okay. Okay, so the branching bound. Essentially, so let's say that we have this problem that is defined on like over a space, like over a two-dimensional space. We have three different inequalities on that space, and we have a restriction that both of our variables have to be integral. The set that we are considering is limited by this solid straight lines. So our interesting, like our point, the points that belong to our set are this, like this points over here, inside of this outline region. We would like to solve this this problem with just the normal algorithm based on the idea of branching bound, the LP algorithm. I'm saying, so it's important to understand that there are multiple algorithms that you can construct out of branching bound idea. But most commonly, you would use an algorithm that is based on LP relaxations, where like at each node you're essentially solving an LP relaxation. So how to start this process of branching bound, how it normally works. The LP version of it is solving the LP relaxation of the problem. In this case, it's the solution to the problem is x1 x2 equal to 20 over 7, 3. So it's this point over here. The upper bound that we get from this solution is 59 over 7, and the lower bound we are not getting because it's not a feasible point. Therefore, like so far we have got only one node. After that, according to the branching bound algorithm, we need to branch our initial node into subsets. Since I would like to stop and say that I ask you essentially, how do you solve, like how to obtain this x1 x2? Like if you have a problem of this sort, how do you obtain this x1 x2? Very interesting problem. Simplest algorithm is an option, but you have only two variables here, and you can actually plot. Yeah, it's just graphically solved. You just need to draw a vector. Yeah, in which you would like to move, and then you move the front as far as possible so that it still has an intersection with the domain. Yeah, so it's an easy task, and I think you should be able to do it even during the exam, right? Yeah. Okay, so branching um, on the the only variable that we should branch on here is the first variable, just because it's fractional. So branching on the first variable consists in adding, like, basically adding a constraint, but it's actually you're adding it twice. So you from one problem you get two problems. In each of them you have added a constraint, but that constraint is different depending on which problem you're talking about. So in the first case, you're adding a constraint xj less than or equal than the flooring of xj bar, and in the second case, it's xj greater than or equal than the ceiling of xj bar. Xj in our case it's like the x1, right? So therefore we are like the flooring of 20 over 7 is 2, and the ceiling of 20 over 7 is 3. Therefore, the two constraints that we are adding are x1 less than or equal than 2 and x1 greater than or equal than 3. We are getting the two, like okay. So how to plot this on our picture? It's this, like, these are the two constraints that we are adding. In one case, let me go to next. So we have a picture like this. Right. So this is our picture. This is x1 less than or equal than 2, and x3 greater than or equal than x1 greater than or equal than 3. Our first like the set that corresponds to our first subset, the subset S1 is this set, basically. Where's the second set? Yeah, it's all the way over here, right? So this entire, like, our point was here, and this entire section of the space just completely disappears from our consideration. Then we need to, after we have made the branching, we need to choose a node that we consider next. In most of the cases in practice, there is a specific rule how you choose, and we have considered some of these rules. For example, we have considered a rule that makes you to choose a point, like a node where you have like the best upper bound or the best lower bound or whatever, or the point that, like, there are different heuristics for that, but in our case, like most commonly we'll be choosing the node randomly, like just arbitrary choice. We have chosen the node S1, and we are re-optimizing. Re-optimizing meaning that we are solving our problem once again. Now with this additional constraint. So x1, 1 and x2, 1 are the solutions for the LP relaxation on our first node, and its values are 2 and 1/2. On this picture, it's located over here, right? So now on this picture, it's located over. Okay. Okay, and the corresponding upper bound is equal to 15 over 2, which is again only an upper bound, and we don't have a lower bound really. After we, yep, is there? Which two constraints you want to add?
The constraint is x1. Why don't we add a constraint of x1 and then solve the problem to x1?
The thing is, if you add a constraint that cuts off um, this entire region, your problem stops being convex,
Okay.
right? It's not an easy problem anymore, and it's not going to be like
Even if there's a limit for random.
well, you will not be able to add just add a constraint, like a constraint having like you will not be able to have a linear program if you have a constraint that separates that cuts off a region that makes your feasible set non-convex, right? You would need to basically how you would do it. You would add a constraint either x1 is greater than or equal than 3, or x1 is less than or equal than 2, and this constraint is or, which means that you would need to introduce a new variable y, which is binary, and that would decide which of these constraints is active. Then you would need to basically add a large number m that is saying like basically that is bigger than any of the numbers in our problem. You would need to say that either x1 greater than or equal than 3 plus y m, or x1 is less than or equal than like whatever, and this y is going to be deciding whether or not a particular constraint is active or not. It's kind of like it's like it would not make your problem much more difficult, just because our variables are all already integer. Nobody cares. But it wouldn't simplify it properly. And there is virtually no guarantee that this approach would lead you. So like you can assume that you relax that new problem once again, and you can try to resolve it or whatever, like with a linear relaxation or something. But that wouldn't necessarily work at all. Like it could work. I think there could be scenarios in which it works, but there is no proof for convergence. This thing converges, like definitely. You definitely will. Eventually, you will split your entire space into enough pieces, and you will solve each piece, and you will find a solution. It might take time, but you will do it. And while if you do this, it could just never converge. But that's a good question. Any other questions here? Okay. Here I want to say that so we are adding a new upper bound for S1, and we do not add a new lower bound for S1, essentially because we don't have any feasible solution at this point, and all bounds are bad for us at this stage. Then we decide to branch. We could actually, instead of branching at this point, we could have decided to consider the node S2. We could do it. We could try to get a better bound for a node at S2, but for now we don't do it for whatever reason. Just our algorithm works like this, and we decide to branch. We branch on, like, first of all, S1 cannot be pruned, and we decide to branch, and we have to branch on the second variable, because the second variable 1/2 is fractional for us. After we have branched, we have x2 less than or equal than 0 and x2 greater than or equal than 1. That introduces for us two new cuts. One is over here, and the other is over here, right? So now we will have two subsets. So this entire area is our S1, and now we split it into two parts. The one part is over here, which corresponds to S4. And the other part is S3 that corresponds to what? Just this small part. Just this piece of line, right? Okay. Then we choose the node arbitrary once again. We choose S2. The resulting linear so S2 is this part, this piece. Obviously, there is no feasible point over there because everything that is feasible is over here, right? So there's no feasible points. There are no feasible points to the right from our x1 greater than 3, and therefore the corresponding linear program is infeasible, and the upper bound is equal to the lower bound is equal to minus infinity, and therefore S2 can be pruned by infeasibility. So S2 leaves our consideration. We don't branch it anymore. Then we need to choose a node once again. We arbitrarily choose S4. We are re-optimizing, and our LP solution is x4 equal to 1, which is this point over here, or on this image it's located over here. X4 bar is integer, and therefore it provides us not only with an upper bound for S4 for the node S4, but also with the lower bound S4. We need to note it. So we update our best lower bound that is known so far to the maximum between z lower bar and 7, which is 7, because z lower bar is minus infinity. And now S4 is now pruned by optimality. The only node that we still have not considered is the node S3. We're re-optimizing for that. We are finding a point 3/2, which is located over here. Its value is equal to 6, which is lower than our lower. So its value is the upper bound for the value of Z3, right? And it's lower than the lower bound for the entire problem. Therefore, we can apply the rule of pruning by bound. There's no way that on the entire Z, like S3, there is a point that is better than for which the value is better than 6, and we already know a feasible point for our original problem for which the value is 7. Therefore, there's no point with a greater value there. Anyway, we can prune it out. And that brings us to the following eventual tree of a branching bound, and this is basically what like how the solution should look like. This finishes our consideration of this problem. Yeah. Any questions regarding that? Okay, cool. So then we have an exercise 783 that, by the way, asks us to show. So we are facing a problem of a binary knapsack. We have all AJs and CJs greater than 0, and we need to show that if C1 over A1 and so forth, Cn over An greater than 0, like the following, like this are really not, these are not very important constraints. They are just saying that the problem is not trivial. It just says that it's possible to satisfy the condition, and also not any vector can satisfy the condition. The solution of the LP relaxation is xj equal to 1 for j from 1 to r minus 1, and then xr is equal to this following number that can be fractional, and then the rest of xj's are equal to 0. If you remember my talk regarding the greedy algorithm, this is basically what the greedy algorithm was given to us. Just we need to remind what exactly was happening there. we were sorting out our variables from 1 to n, so that the relationship between C1 and A1 is being decreased. We are like this relationship between C and A is basically the cost of a unit of volume that is being occupied by an item, right? And then we are just taking the items one by one. We are going on our through our list of items from 1 to n, and we are picking up the items if we still can fit it into the backpack, which basically corresponds to this like approach. But at some point, if we are not able to fit something into our backpack, we do not throw it out and like just skip to the next one. We are taking a fraction of our item, right? Which is basically like corresponds to very much the same idea. And this allows you to solve the backpack, the knapsack problem using LP relaxation, even if the number of variables of the problem is much larger than 2. And it actually allows you to like solve any kind of LP relaxation for knapsack problem very efficiently. Let's see how we can solve the instance of the problem consisting of 4 variables by a branch and bound approach. So our first, so let's say that our B dash is the amount remaining from B when fixing the lower bounds on variables. When the lower bounds on variables are taken into account. So the first node that we need to construct, let me actually, I don't think I'm writing it down now. So the first node 1 corresponds to just a linear relaxation for this problem itself. How to solve it? How do we solve the linear relaxation for this problem? Well, we just note that 17 over 5, and then we have 10 over 3, and then we have 25 over 8, 5 over 8, which is greater than 17 over 7. 17 over 7. So our variables are already lined up. We don't really need to change anything. And then what we did is we are picking up the items like completely, like the whole items as much as we can. So we are taking the first item because it can fit into the backpack. We can fit the second item. So our first 2 variables are going to be equal to 1, and then the third item cannot be put into backpack like together. Like the entire item cannot be put into the backpack, and therefore we just take half of it, and then the rest of the variables are going to be equal to 0. So our solution to the LP relaxation is equal to this thing. Are there any questions regarding this? Regarding how we we branch on the variable x3 because it is a fractional number, and that brings us, so our ZLP, which is the upper bound for our solution, is 39.5, and the lower bound is minus 70. Then we branch into 2 branches. The one of them is the node 2, the other is the node 3. And the branches correspond to x3 being equal to 0 and x3 being equal to 1. The node 2 is so let's consider the node 2. The solution for that node, once we have zeroed out this value, we don't like we essentially we cannot take it anymore. Therefore, the first two values remain to be equal to 1. The third value has to be equal to 0, just because the additional bound that we have added, and then the third value has to be equal to 4 hours. This is our new XLP. So it was XLP1. This is XLP LP2, and now we need to branch on the fourth variable. So that creates for us two new nodes 4 and 5. The node 4 corresponds to x4 being equal to 0, and node 5 corresponds to x5 being equal, x4 being equal to 1. The LP solution for the node 4 is 1100, which is the first feasible solution that we encounter, and the corresponding ZLP is equal to 27. And by the way, the corresponding ZLP for the node 2 was 36 and 5 over 7. And so the new best lower bound that we have is also equal to 27, and that needs to be propagated backwards. Therefore, it's also for this one 27, and for this one also 27. Okay. In node 5, x4 is equal to 1 implies that first of all, b dash is equal to 5. Therefore, x3 must be equal to and essentially x3 is equal to 0, and x4 is equal to 1, and the corresponding LP solution is 1001, which gives us a new lower bound 34. We also pruned, so the node number 4 and the node number 5 both can be pruned by optimality at this point. It's important to note how exactly we so our B is like it used to be equal to 12, and now we have reduced it to be equal to 5, just because our x4 now is being equal to 1, right? So our b dash is like has changed its value, and now it's being equal to 5. Therefore, this solution is exactly the LP solution. After we have updated the lower bound for the node 5, we can update it also for node 2, 34, node 1. And the only thing that we need to consider now is the node 3. In the node 3, x1 must be equal to 1. X3 must be equal to 1, which implies that x1 and x4 must be equal to 0. Just because if x1 is equal to x3, if x3 is equal to 1, then our like bound is like has been reduced from being 12 to being 4, and therefore like the only item that can be still put into the backpack is the second item. And that brings us to this brings us to a conclusion that like ZLP is equal to 35, and the new like lower bound is equal to 35, and we can prune that that solution by optimality as well. And that concludes our entire solution for the 0-1 knapsack problem. I hope that it was clear how exactly I was solving this LP. Are there any questions, Roddy? Okay. And I just wanted to point out that similarly you can solve knapsack problems for like more general like non-binary knapsack problems as well. You just need to take as many items as you can, just because at any node you need to set xj being less or equal than b dash over aj, and basically you still need to order your items after that. And you need to take as much of an item as possible for your purposes. I would say that here in node 3, it's important to note that that you still have like strictly speaking, you would need to like, if you were to just follow the exact algorithm, you would need to actually still branch the node 3, because here our value x3 being equal to 1. So not 3 corresponds to x3 being equal to 1. If x3 is equal to 1, then on the right hand side you still have 4, right? You still have a capacity of 4 to fill up. And if you strictly follow the algorithm of solving the LP relaxation, you would need to say that you would still obtain a fractional solution where you have a fractional number on the first place, and then that it would be 0, then 1, and then 0. Then you would branch on the first component into two nodes, and then you would like one node would correspond to x1 being equal to x1 being equal to 0, and then that node also would be branched into 2 according to x4, and only that node would be already the final one. So there is some sort of like inconsistency in this particular example. So if you were like if you try to solve it yourself, if you continue solving it, this is basically the picture that you would end up with. Anyway, I will like if there is a problem like that, I will try to keep the size of the tree to a reasonable size. Okay. Let me speak a little bit about the next kind of what was coming after the branch and bound algorithm. So we have seen the different alternative ways of branching. So instead of branching on a particular variable, we were able to branch on a subset of variables, defining a special ordered set. We also have seen ways to exploit the symmetry of the problem, introducing the orbital branching. And also we have seen ways to try to, so like basically we have seen a way of like ways to reduce the size of the problem that we are solving by applying some pre-solving techniques and strengthening the formulation of the problem that we have. So by basically adding more constraints, or even like reducing the number of variables. All of that is like our examples of like pre-solving. And we have seen a couple of pre-solving examples that have given us the following kind of sets, like a set of rules that we would need to follow if we were to like add or like add more constraints or reduce the number of variables, like fix the values of some variables, or getting them as redundant. Basically, like these rules correspond to, I'll like, since we have discussed all of them, I will not stop on them individually. I just want to say that there's some like pretty generic like linear algebra kind of pieces of knowledge that you can use for your own like methods of strengthening the formulation, and you might want to use them before you start your linear programming or branching bound algorithm, before you start approaching your problem by a branching bound problem, because basically in some cases it's like instead of having several branches, it's enough to add several valid inequalities in order to understand that that the problem is actually much smaller in size than you have it initially. So this LP pre-solving and also the IP pre-solving techniques are quite important, and I suggest you to review the exact like points on this list, how exactly we were doing it. We have seen also the strengthening inequalities. They are a little bit more complex, but still it's like they are an important example. I don't think that there would be any specific problems on the final regarding strengthening inequalities, but they still might be useful in some of the subtasks that might appear there. Yep.
So all inequality is pre-solving. Those are just techniques that we do. The formulation would be
Yeah.
Well, while also making sure that all it's like we have a big problem set. Maybe there's like some like super formulation that has like really big and it perfectly encapsulates the problem. And then there's like a better formulation which is like smaller spaces. And then this pre-solving and development of accounting, so you have something that's much more manageable, and then that problem itself, we just solve that problem. That's going to be like
exactly, yes. You're right. Let me show you like a picture. Okay, let me show you a picture to illustrate that exactly what you're saying. So over here we have had this. Just one second. Where we were discussing. Yeah. So looking at this picture, you can see that, for example, this formulation over here, it is, in a way, it is simpler than the exact formulation, because, for example, it consists of a smaller number of inequalities, right? Like the bigger formulation P1, it has only four sides, so it has a smaller number of inequalities that describes that, while the one that is actually a better formulation, yeah, the exact formulation, the best formulation, it has like a larger number of fake sets. So it's yeah, and it's obvious, it's often the case that the exact formulation is going to have an exponential number of inequalities. Therefore, it's not like it's not necessary that that IP is like the corresponding IP is going to be NP hard, because it could be that all of the it could be that all of even if your set if your feasible set is extremely complicated, has like very an extremely large number of inequalities, it could be that you are only into like the set of problems correspond only to the cases when when you hit a small portion of that of them, and you only need to like do a search over a smaller subspace. And complexity is not directly related, like the computational capacity is not directly related to the number of face sets in the exact formulation. But it's often correlated. Like definitely, if you have a small number of simple inequalities in your exact formulation, then the problem is going to be easy. Yes, and basically, when you are reducing the size of the problem, when you are adding valid inequalities, you are cutting off some of the weird points that you might end up with if you are doing branching bounds straight away, right? Like for example, you might add an inequality of this form, and that would reduce the number of possible branching bounds and bound steps that you would need to take. Okay. Regarding the branch and bound inequalities, regarding the valid inequalities, right? So we have seen the examples where we are adding the valid inequality is an inequality that is valid for our entire space. And we have seen the examples and like how to add the valid inequalities in the cases when we have particular types of fairly common problems and fairly common formulations. How to utilize the fact that we can round up or round down our coefficients, just because the corresponding variables are integer valued. So for those purposes, we have had those the valid inequalities that you definitely need to remember. And as a combination of all of that of that story, we have had this CG procedure, CG inequalities that kind of make up the entire set that you need, of the inequalities that you possibly can utilize, that you possibly can use in order to construct valid inequalities for your set X. And the first two are the inequalities that are valid even for the P, for the formulation itself, that has a particular structure. And the last inequality is the inequality that is valid for X. What's the difference between inequalities that are valid for P and the inequalities that are valid for X? Is the question clear? For example, if we see this picture over here, our feasible points are the lines, the bold lines, and then we also have a valid inequality. Where is our P in this case? What would be the valid inequality for P, and what's the valid? Right. So it's the set of all reals that fall into this this set, right? Like over here, this entire space is the P, including this little triangle. Like this little triangle is also in P, while the set X is only these lines. And this inequality that is being highlighted, the Wallis inequality, like this one, is a valid inequality for X because it doesn't cut off any points from X, but it does cut off the points from P.
Basically, the valid inequality is cutting off until only the cut off any part. The cut off more.
Yeah. But like an inequality, for example, like this, inequality like this, would be valid for both P and X, and that's something that you can construct just using this two CG inequalities over here. Yeah. So this two are constructing valid inequalities for P, and this one constructs inequalities for X, but altogether they can construct any inequality for X just by combining them together. Right. This is something that has been proven during the lecture. I think it's the lecture 2 weeks ago. And that gives a rise to the idea that, like, since by combining these two kind of pieces of inequalities, we can get any valid inequality. That basically means that we can have the convex whole of, like, for any complex set just by combining this inequalities between one another. And once we have the convex whole, we can just solve the LP, and that will bring us the solution. That gives a rise to a new idea of how we can solve IP problems. We can just keep generating valid inequalities until we have constructed the convex whole, and then once we have done that, we definitely will solve the problem. Actually, we might be able to solve them even faster, even before constructing the actual convex whole. If we just were able to construct, like, for example, if we have an integer point, and then the original formulation have had two inequalities like this, probably we were able to narrow that down to two inequalities that actually have that as an extreme point. And then when we solve the problem, we end up at this point, and it turns out to be feasible, and that's it. And we are done. So we are really interested in a situation like this, and that gives us an idea about the cutting plane method that is based exactly on this. Let's say that we have the P is a formulation for X, and we have curved F is the set of additional valid inequalities for X, possibly an exponential or an infinite cardinality set. For example, it could be the set of all valid inequalities for X. That could be an option too. Then the algorithm goes like this. First, we solve the linear programming relaxation of the problem. We get X tilde, which is the solution of the linear programming relaxation. Then, if X tilde is in X, then we have solved the problem. We can just return X tilde. If it's not, then we should find at least one or several cutting planes, cuts, P0, that we will be able to looking. We will be looking for in set F, such that this cutting planes cut off our X tilde, separating it from our original set of valid points X. We add violated cuts to P, and then we resolve the LP relaxation. So basically, we are cutting off exactly as we discussed it in the beginning of our lecture. We're cutting off points that we do not want the linear programming relaxations to converge to anymore by adding new constraints to our LP. If no such cuts exist, then we go back to branching. But normally, like if your set F is rich enough, then you don't need to do it. Never. So this is not a particular algorithm, but just because it doesn't really tell us what to take as F and how to find this cuts in F. But from that, you can construct more precise, like this is basically an algorithm scheme, and from this, like according to the scheme, you can construct several different algorithms. There are actually plenty of them. One of them is actually the algorithm for the solution of TSP that we have just discussed in the very beginning of the lecture. There is another very important cutting plane algorithm, which is the Gomoris fractional cutting plane algorithm. We consider a problem of like linear integer programming, linear integer programming. We are solving it, and we are splitting our set of variables into two subsets, basic and non-basic, just according to the simplex algorithm or whatever algorithm you use. We know that it can always be done just from the theory of linear programming, and then we add the CG cut, like a CG cut that is constructed so that it cuts off the corresponding solution of the linear programming relaxation just by utilizing the fact that such CG cut always exists. We can always do that, and therefore we will progress through the algorithm. The convergence of this algorithm requires a little bit of effort, but at least we can prove that we will always be able to make a step of this algorithm. Then we have seen an example of the Gomoris algorithm. I would like to skip through it just so that we can discuss a second approach that also utilizes the idea of cutting planes, that is called the Bander's procedure, Bander's algorithm. In that algorithm, the idea is pretty much similar. First, we solve an LP and then we cut off a point, but it's a little bit more specialized. Also, because it can be used in the current form. It can be straight up used for mixed integer programming problems. Especially, it's very important for very useful for the cases when the number of integer variables is lower than the number of real variables. Just to remind you, in the Bander's algorithm, we have had a function phi of x for each binary or pseudo binary variable x. We can define phi of x such that it's a solution of a linear programming problem, given that we have fixed all of the values of the variables x to be a particular value, right? So in this original problem, we just fix this x to be a certain value, and then we solve a linear programming relaxation and see what happens. So this is how we decide, and the corresponding optimal solution is denoted as phi of x. And then we have realized that since this phi of x is a linear programming problem, we can dualize it. We can and the solution of the dual will be able to will be equal to the solution of the primal. And then we realize that the solution of the dual can be expressed in a few different forms. And one of the most interesting and important forms is the one that has description through the extreme rays and the extreme points of the set U. It's very important to remember what exactly the extreme rays and the extreme points are, and be able to distinguish between them. Using this extreme rays and extreme points, we were able to formulate the master problem for mixed integer programming problem at hand, which the solution of this problem over here is equivalent to this, exactly equivalent to the solution of the original problem, but instead of having a lot of real valued variables, we have a lot of constraints. And now, since we have this huge number of constraints, we can actually discard some of them and try to keep adding them manually through an iterative procedure, looking for a subset of inequalities that are actually important for us, instead of having to consider all of them at once. That brings us to the Banders procedure that has at its core the solution of LP linear programming problems over the set U that has been introduced over here, which is the dual feasible set for the problem that is defining phi. And then we have seen that there are different cases that the second step of looking for phi of x can lead us to. It can lead us to finding new extreme points or extreme rays of U. It can also lead us to basically a necessity to actually prune our problem into adding and to adding new branches to our branching tree. We have considered an example of this Banders procedure. I would like to present you with a different example. But if you have any questions on the general algorithm, I think since we have kind of revised it just now, probably you have any conceptual questions regarding it. No questions for now? Okay. Okay. So here is the basic branch and cut kind of idea described. You have a problem of two variables and two general inequalities and two non-negativity inequalities. Its feasible region is described on the on the right. So basically, yeah. So I wanted to this is not exactly the example though that I was looking for. Anyway, this is about this is a valid example of I think okay. So instead of this example, I would like to come back. It's probably better to take a look at the example of the Banders algorithm once again, because it's it's a general purpose example, while the Banders algorithm is a more specialized. So in the Banders algorithm, we have had a dual picture like this. We have had a dual set U that looked exactly like this, and it had the two extreme rays and two extreme points, and three extreme points, and therefore our Bender's master problem looked exactly like this. To each inequality, there was to each of the points of the extreme points of U and extreme rays of U, there was a specific inequality in the master in the master problem that it corresponded to, and also there was a description of the feasible set X that is outside of the description of phi. After we have put this all together, it makes easier. So this view of the master's problem makes it much easier for us to try to solve this problem. Just because from now on, every time we are able to find a new up to like a new extreme point or extreme ray, we can just come back to this master problem and pick a corresponding inequality in order to add it to our problem, right? Normally you would not. So like this is not how algorithm works, right? It's not like you Bender's algorithm never really lists out all of the inequalities and all of the points. It kind of generates it, but since it's us being like solving this problem by hand, it's easier for us to formulate the master problem in advance. Are there any ambiguities regarding how to solve for phi of x in this case? So there are two kind of approaches to solving for phi of x. As you can see in this particular example, we have three variables. Sorry, we have three primal variables, y1, y2, and y3, and we have two dual variables. Therefore, it is kind of easier for us to try to solve the problem for phi of x in the dual space and not in the primal space. But you can also try to solve it in the primal space if you would like to. Hello. Okay. Let me know if you have any questions. We will stop here. Please do make sure that you repeat the topics of cutting planes and Bender's algorithm. And I wish you all the best for the RRR week. I might not be able to see you on the final, but I will be on the call. So the final might be held for you by the reader, and then but anytime before the final, please feel free to reach out to me if you have any questions. Yeah, so it's before it was just one cheat sheet. At this point, it will be two cheat sheets because one from the midterm and one that you might want to prepare for the final. I'll do my best so that you do. That's a great question.
Do you have any formal upside plan?